Radio, kia ora koutou. We're looking at, so this is part of your 6? Yeah, 1.6 geometry. We've got these exterior and interior angles of polygons that we've got to deal with. So, tons of different angle rules in this topic. And this is our next one. Okay, so interior and exterior angles. Interior, of course, is like the inside. Oh, I need my draw thing on, don't I? Inside whare, interior angles is the inside, okay, just like an interior designer. Your exterior angles are outside, okay, like exit, they're on the outside, ki waho, outside. So they're exterior. So exterior angles of polygons. So we're talking about polygons, they've all those shapes with straight sides, and they all, all those edges meet at vertices. So we're talking about what happens with those angles that are all the way around the outside. So exterior angles, when they say that, what they're meaning is if you turned your shape, so like this thing here, it's just a pentagon. Oh, sorry, mate. I've got this fancy new computer and I'm just getting used to how the stylus works. So we've got this pentagon here, and it's the idea as if we turned our shape into like a, those spinny things that you get at fireworks, and it sprays fireworks, a Catherine wheel, that's the name, and you put a nail, you attach to the fence, and you go, that's what I think of when I think of exterior angles, okay? So it's as if each side just carries on, it goes a bit longer, it goes out longer than the corner, than that vertex. And then we're looking at those little angles that you get in between that long line that you've made and the next edge of the polygon. Okay, this one here that I'm going to do in blue, these ones, we know what that angle is there, don't we? Because it's a straight line, so it's always 180 degrees. So we're not talking about him, we're talking about these wee green guys here. Okay. Oops. Oh, did that in blue. What's happening here? I'm clicking on different things. Okay, these wee green ones. They're always going to be the same for regular polygons, okay? So if you've got the same length sides and your interior angles are all the same, so a regular polygon like a square or an equilateral triangle, then those exterior angles will always be the exact same size as each other. But they will always, which is very cool, and they draw it nicely here, they'll always add up to 360, okay? And that's the beautiful thing about exterior angles. They will always add up to 360. So if we have a look at this polygon here, we get smaller. If we make it smaller and smaller and smaller and smaller, bringing them in, you end up with this guy here that looks like a basketball. So these 5 angles that you've ended up with, they have to add up to 360. So if you're talking about a regular polygon, then it's going to be nice and easy to calculate, because for this case here with a 5-sided polygon, you can just do 360 divided by 5, okay, if it's regular. If it was something like a regular octagon, you would do 360 divided by 8, because you'd end up with 8 exterior angles happening, okay? But it's always that they'll add up to 360 degrees. And so that, when you're dealing with these angle properties, that is a super handy thing to know. And you can use that. You might be given some sort of polygon and you're working with angles that are on the inside of it, and you've gotten to a point where you're really stuck. You can then go, actually, if I extended this straight line out here, then maybe I can work out what this exterior angle is, and then maybe that will help you to work something out, okay? So they're handy wee things. The next type is the interior angles of the polygons. So this is inside, like you're an interior designer. And this is quite clever. So many of you guys in TNA did this last year. So I'm mainly making this video for the benefit of those that weren't in TNA last year, or if you're away when it was taught or you don't remember, whatever. So interior angles, we are working out how much do those angles inside a polygon add up to. So you guys will already know You already know, for example, that the angles inside a triangle, those three angles in the corners, always add up to 180 degrees exactly. Same with your quadrilaterals. You might have a rectangle. Those angles, and for a rectangle, they're all right angles, so they're 90 degrees, they'll always add up to 360. Okay, and that, of course, with that quadrilateral, it doesn't matter what type of quadrilateral it is, those angles will still add up to 360 degrees. Then we actually get a bit of a pattern developing. So if we now went to a pentagon, oops, what an awful pentagon that was going to be, 3, 4, 5. Those interior angles that you end up with there on the pentagon, so this was 3 sides, this was 4 sides, this is 5 sides. If there was a bit of a pattern going on here, what do you think that next one would be for a pentagon? It'd be adding on another 180, wouldn't it? So we end up with 540 degrees for a pentagon. Each time we add on a side, we're going to add on another 180 degrees. And the reason for this is that you can make each shape out of triangles. The triangles are 180 degrees. So check it out, a quadrilateral, you can actually make that out of 2 triangles. So 360 degrees, because you know that and that and that are all 180, plus that and that and that, another 180. Okay, so 3 lots of 180 would make a pentagon. Okay, because we can fit 3 triangles out of that pentagon. Okay, we're at a hexagon, 3, 4, 5, 6, 1, 2, 3, 4 triangles that we've got going on there. Okay, so we end up with 2 lots of 180 degrees for a quadrilateral, 3 lots of 180 degrees for a pentagon, 4, 5, etc. If we wanted to then generalize what's going on there with that beautiful pattern, we might say, okay, well, what if I've got some massive shape with, 50,000 sides, and I want to work out how many degrees it's going to actually, all those interior angles are going to add up to. I could just use I could use that pattern and use a bit of a formula to do that. So how about we call it n for any number of sides on that polygon? Well, hopefully you've had a wee look, and can we notice a relationship between the number of sides and how many lots of 180 there are? So maybe I should do this in a different color. So like a pentagon was 5 sides, we used 3 lots of 180. Quadrilateral was 4 sides, it was 2 lots of 180. 7 sides for a heptagon or a septagon, 5 lots of 180 for that. So hopefully you're seeing a bit of a pattern. Hey, so if it's got n sides, what number am I going to have to multiply by 180? 7, 5, 6, 4, 5, 3. I'm taking away 2 every time, aren't I? So I'll end up with n minus 2 lots of 180. So if I had a 50,000-sided polygon, I could do 499,998 times 180. And that would tell me what those interior angles of the polygon add up to. Rightio, so those are our interior angles, and then we can use those properties when we're doing any of these gorgeous little angle problems. Okay, so let's have a wee look at an example here. So this is also from our Walker Maths geometry book. The diagram shows a regular octagon. Calculate the size of theta. All right, so we've got a regular octagon here. All those sides are the exact same length. So all those interior angles are going to be all the same size, as will all of those exterior angles. We talked about the exterior angles. They always add up to 360 degrees. All right, this is an octagon, so he's got 8 sides. So we can just now divide 360 by 8 to work out what that, if we made up a little Catherine wheel, to work out what that little angle in there is for each one. So let's do that. 360 divided by 8. Okay, remember our fraction, top divided by bottom, that's all it is. It's a big divided by sign. 360 divided by 8, that gives us 45. So that tells us it's those tiny little exterior angles of 45 degrees each. They're lovely acute angles. And so if we're wanting to find this particular angle theta, it's not just the little 45 degree angle, is it? It actually goes the whole way around. We know that that's a straight line, so that part's 180. So we're going to end up So theta is 180 plus that little 45 degree part. So we end up with, what is that, 225 degrees. Okay, remembering that this is geometric reasoning, we want to provide reasonings for every step that we do. So here, this part here, we have done 360 divided by 8 equals 45. Put there exterior, so you can put it in brackets beside it, because exterior angles in polygons add to 360. You could even write on there that it is, because it is regular, you're dividing by 8. All right, example 2 here, we're working out the size of theta. We're told, how long have I got? Yep, interior angles. Calculate the size of theta. Right, okay, so here we are. We've got this 1, 2, 3, 4, 5. This lovely little pentagon going on there. And then that line is extending out there, and there's theta in there. Okay, we want to find out how big that is. So we look at what we know. Remember, in geometric reasoning, this is what we do. We look, what bits do we know, and then can we find out any more bits? So if we look at this, we've got a pentagon there. It's given us 4 angles, because we've also got our right angle one here. So he's 90 degrees. We've been given 4 angles, so that's great. Straight away we can work out what this 5th angle here is, can't we? We know that interior angles of a pentagon, it must be 5 minus 3 lots of 180. Oh, sorry, that's meant to be a 2, isn't it? I was thinking of the answer, which is 3 lots of 180, which is 540. So all of those angles need to add up to 540 degrees, okay? And again, like they've done in the book, you need to put your reasoning. Interior angles in a pentagon add to 540. You must put those reasonings, and I know it's so annoying to have to do all this writing in a jolly maths topic, but you do. Okay, and so then, right, we've worked out that they all add up to 540. So let's now take away all of those angles that we've been given. Minus 90, minus 99, and we'll end up with, oh, they haven't actually worked it out. We can do that though. So 540 minus 145 minus 114 minus 90 minus 99. We end up with 92. Okay, so this angle here, and we could call it angle A. So A equals 92 degrees. And that's the same reasoning that we've just done there. So angles on a straight line, or supplementary angles, always add to 180. So that means theta must be 180 minus 92, which is 88 degrees. I did a slightly different working to the book. They've written it out a little bit, just sort of combine 2 rules in one. I think it's a really wise idea to work out each step as you go. If you're super confident combining a couple of steps at once, you could, but otherwise just get one part, work out that bit, then go to the next part, then go to the next part. So yeah, hopefully you're sweet. That's interior and exterior angles. And yeah, you can use them to your heart's delight and all of these lovely little problems that you've got coming up next. All right, thanks.